decades and how that can inform future development of future technologies. So with that, Micah.
Thank you for that introduction. Can you see my slides?
Not yet.
I think it's pausing my screen sharing. Okay, we will try this again.
So it looks like
could the host allow my screen sharing to be unpaused?
It says started screen sharing, but then it sort of stopped.
Okay.
Sort of crashed right away.
Let's see if we can do it this way.
Okay.
Okay, you should now be able to see my screen, correct?
Yes.
The slides?
Yes, perfect.
Thank you so much. And thank you for the introduction and for moderating our discussion. Today, I would like to describe some of our research to identify strategies to accelerate the improvement of energy storage technologies. In particular, we studied lithium-ion batteries to learn about the factors that influence their improvement. During this talk, I will share the results of our investigation into the determinants of improvement of lithium-ion batteries and the resulting quantitative insights that can inform decisions moving forward. So everyone should be able to see my second screen at this point, or my second slide. And on it, we're going to start with a few of our goals for energy storage technologies. Energy storage technologies have some critical roles to play in our transition to sustainable energy systems, including in the electrification of our transportation, our cars and our buses, and in the integration of renewable energy resources into the electricity grid. And these roles are crucial. If we, let's say, examine greenhouse gas emissions by sector, we see that a considerable percentage of our current emissions, about 43%, come from transportation and power. And of course, the power sector is expected to play an even larger role as we electrify additional energy services to enable decarbonization. Lithium-ion batteries are already starting to play both of these roles. Meanwhile, other nascent energy storage technologies are still being studied and developed. And in addition, other established technologies like pumped hydroelectric are seeing newfound deployment. All of these options might be able to complement each other in the roles that they play. However, the further adoption of lithium-ion and these other storage technologies will depend in part on how rapidly they come down in cost and improve in other measures of performance going forward. And we have limited time and limited resources to develop and deploy these technologies to address climate change. So we want to know, how can we, given our limited time and resources, make and deploy batteries better, faster? This question falls into a broader research agenda in which we seek to understand why technologies change so that we can inform strategies to accelerate our transition to sustainable energy systems. We're trying to figure out what drives technological improvement and deployment. Why do some technologies improve rapidly while others do not? How can we better direct research and development, design public policies, and inform investment strategies? In this work, we're trying to answer these questions with regards to energy storage technologies, in part by studying lithium-ion batteries. So, what can we learn from lithium-ion batteries? Well, I'm showing a visual progression of their improvement on the top of this slide, from a test tube cell in 1983 to the first commercially produced cells in 1991, to a large stationary facility in 2018. In all of these cases, the shuttling of lithium ions back and forth is used to store and release energy. So lithium-ion batteries appear to be improving, visually at least. But the first question we want to ask is, how quickly have lithium-ion batteries actually improved? Are they a good model to study if what we want to learn is how to rapidly improve battery technologies? And then if they are a good model to study, if they have improved rapidly, then what factors led to this improvement? And what lessons can we learn? Then thinking toward the future, how can we enable further improvement for energy storage technologies? What should researchers, policymakers, and businesses do? I'm going to describe our research to answer these questions. And in it, we're going to apply some key methods. We're going to collect extensive empirical data sets. We're going to use explanatory models to understand why technologies change. And we're going to identify robust insights that can improve decision-making. Let's start with the first question. How rapidly have lithium-ion batteries actually improved? Well, we were not the first researchers to investigate how quickly these technologies improved. Others have investigated how, for example, the prices of lithium-ion cells have changed over time. And I'm plotting the data series that they've used here. I should note here that we, as well as previous researchers, are using price as a proxy for cost, because battery manufacturers rarely, if ever, publicly discuss actual production costs. As you can probably tell by looking at the data that we've collected and plotted here, we found widely varying estimates of the price decline of lithium-ion cells. I'll note that the y-axis here is logarithmic. There are large absolute differences between the prices that different researchers used for lithium-ion cells in the same year. And when we go on to estimate the annual rates of price decline for these different series, we find that they range from 9% up to 29%. This data uncertainty makes it hard to know how rapidly lithium-ion batteries have actually improved. And if these data were used to project future price declines, we get many diverging projections. The underlying data uncertainty leads to these wide ranges of estimates as to when lithium-ion battery cells might reach certain cost targets. So we wanted to develop improved estimates of the price decline of lithium-ion batteries. And the results of that effort are plotted here. We find that the prices of lithium-ion cells decreased by 97% between 1991 and 2018. We determined this by collecting as much data as we could from previous researchers and from other sources not yet used. We went back to original sources whenever possible. We ended up harmonizing 25 different data series, 68-point estimates, and importantly, we categorized them. So lithium-ion batteries are manufactured in a variety of shapes, and we separated the data based on whether they referred specifically to cylindrical, prismatic, or pouch cells, or whether the data referred to all types of cells or were otherwise non-specific as to what they referred to. And you can see in this plot here in blue, I'm showing the data that refers specifically to cylindrical cells. And in orange, I'm showing the data that refer to all types of cells or are otherwise non-specific. And within these two categories, we had enough data to develop representative series, which I've plotted here as these bolded dashed lines. Using the best available data from any given year, we can develop an estimate for that year. And we can follow these representative series and see, for example, that there's a considerable difference between the price trajectories of cylindrical and all types of lithium-ion cells. And these representative series can be used in top-down studies of cost change. So what do I mean by a top-down study? Let me briefly introduce two sets of methods we use to examine technological change. The two sets of methods are phenomenological models and mechanistic models, and these approaches are complementary. The phenomenological models are top-down. They require some high-level data on technological progress and potential drivers of that progress, and they can be used to measure rates of technological improvement. Meanwhile, the mechanistic models are bottom-up. They require a cost equation and detailed data on the design, the engineering, the manufacturing, the prices of different components, and they allow you to quantify how changes in individual components contribute to change in a technology over time. Over the course of this talk, we'll discuss the application of both approaches to studying the improvement of lithium-ion technologies. But we're going to start with the phenomenological models, which typically take the form of the equation shown here. They require the high-level data on technological progress and drivers. And they typically take the form of this equation where on the left, we have the measure of technological progress. So for example, the scaled real cost of a technology, where scaled simply means we've taken the cost of the technology and divided it by what the technology provides. And real means we've corrected for inflation. On the right, we have potential drivers. For example, we can look at the relationship between technological progress and time. Colloquially, we refer to this as Moore's law. And we're not saying that if you take a battery and put it into a closet, it just gets better with time. What we're saying is that time is a proxy for different activities that take place over time, like research and development. We can also look at the relationship between a decline in cost and the increase in cumulative production. Colloquially, this is referred to as Wright's law or Wright's curve. And when we use this to measure an improvement rate, we get an improvement rate many of you might have heard of before. This is the learning rate, which is the cost decline observed upon a doubling of cumulative production. We can also look at annual production or cumulative research and development activity, which is sometimes approximated by the number of patents filed. But if we want to measure these rates, we need to understand how these potential drivers changed over time. So, for example, we collected data on the size of the market for lithium-ion batteries, which we're going to use as a proxy for the production. We found that market size increased by over 4 orders of magnitude since the early 1990s. We collected and harmonized 30 different data series, categorized them by cell shape, and developed representative series. We similarly collected data and harmonized data on patent filings, but because many patent filings could apply to different types of batteries, we couldn't split them into subgroups based on cell shape. And so now, given our representative series, we can fit those models of technological change. Here I'm showing the results of analyzing the decline in price versus time, price versus cumulative market size, and price versus cumulative patent filings. We find that the models all fit relatively well and that price decline is nearly exponential with time. In orange here, I'm plotting the data for all types of lithium-ion batteries, and in blue, I'm plotting the data just for cylindrical cells. And we can measure our rates of improvement for example, when we look at improvement versus time, we find that the prices of both all types of cells and cylindrical cells fell at a rate of about 13% per year. Meanwhile, we find a learning rate for all types of cells of about 20%, and that for cylindrical cells around 24%. So we had a sense that these improvement rates were more reliable because we resolved some of the underlying data uncertainty. However, we also thought they might underestimate how rapidly these batteries actually improved. And that's because lithium-ion batteries were not adopted because they were the least expensive option available at the time. They were adopted because they allowed you to hold a camcorder in the palm of your hand, or a cell phone, or a laptop, or a power tool. They were adopted because they allow you to have a lot of energy in a limited volume. They have high energy density. And so we wanted to figure out, is there a way to consider improvements along this dimension, as well as a decline in price, when we're measuring the rate of improvement of the technology? So let's take a look back at the original model and examine the definitions we used. If we take a look at our measure of technological progress, and we can kind of think about what we're saying when we look at price per energy capacity. When we look at this, what we're kind of saying is that we're looking at the cost or price of a technology and scaling it by the service a technology provides. And when we just look at price per energy capacity, we're saying energy capacity is the service provided by the lithium-ion cell. But we want to consider other cell level attributes. So we decided to apply a multiplicative model. We're proposing this as a model that is as simple as possible or as parsimonious as possible, that still captures the effects we're interested in. We are going to estimate the service per cell as the product of different cell level attributes weighted by exponents. So if we want to incorporate another metric like energy density, we could say the service per cell is the product of the energy capacity of the cell and its energy density. Once we define service in this way, price per service, it follows naturally, and then we can come down to the bottom equation for price per service. Because we don't have additional detail on how these different characteristics were prioritized by people who purchase these batteries for use, for example, in electronics, we're going to set the exponents equal to each other and equal to 1. We can then think of price per service as the product of 2 different types of prices: a monetary price you pay for energy capacity and a volumetric price. And so we can estimate price per service. First, we need the price per energy capacity series, which we've already developed a representative series for. And then we need a sense of how volume over energy capacity changed over time. Or we can look for its inverse, energy density. And so we ask, how did energy density increase over time? And we return to our approach of collecting as much data as possible. We collected 13 different data series and more than 1,300 data points. We harmonized them, and the results are plotted here. The resulting data show that energy density has increased considerably since the early 1990s and started leveling off a bit since 2010. You might also notice considerable diversification. This diversification reflects the broadening application of lithium-ion technologies, that not every application of lithium-ion batteries required the highest energy density available at a given time. But we still wanted to track the improvement of the technology and not necessarily its broadening application. So we developed representative series using the 98th percentile. And given these representative series and the ones that we have for price per energy capacity, we can now estimate how price per service changed over time with our expanded definition of service that includes energy capacity and energy density. And we're fitting those same three models of technological change: the relationship between price and time, price and cumulative market size, and price and cumulative patent filings. And in orange here, I'm showing the results for all types of cells when we have a limited definition of service, just energy capacity. And in purple, I'm showing the results when we expand our definition of service to include energy capacity and energy density. And we see in all cases, we measure substantially higher rates of improvement. Our improvement versus time, our annual decrease ratio, increases from 13% to 70%. Our learning rate increases from 20% to just shy of 27%. So overall, we think these rates might be a more holistic estimate of how rapidly these technologies improved. Our next question is, compared to what? Well, we can compare the rates we've measured for lithium-ion batteries to the rates measured for other technologies. And I'm showing the results of that comparison here. On the left, I'm showing annual decrease ratios, improvement rates of improvement versus time. And on the right, I'm showing learning rates, the rates of improvement versus cumulative production. And these vertical dashed lines are the rates we've measured for lithium-ion batteries with our constrained definition of service, just price per energy capacity. And in these multiple colored histograms at the bottom, we're seeing rates measured for technologies from other industries, chemical, energy, and hardware. And we can see, even with this constrained definition of service, lithium-ion batteries have improved more rapidly than many other technologies versus time, but they're towards the middle top of energy technologies and the middle bottom of chemical technologies. If, however, we expand our definition of service to include energy density, we find that lithium-ion batteries have improved much more rapidly than many other technologies versus time, and now their learning rates are towards the top end of energy technologies and the middle top of chemical technologies. So overall, we've been able to greatly reduce the data uncertainty and reliably measure rates of improvement. And we find that the improvement of lithium-ion technologies, its rate is comparable to that of solar photovoltaics, which is often held up as a prime example of a rapidly improving clean energy technology. So given this, we now want to know, why did this happen? What enabled the rapid cost decline? What lessons can we learn? And to answer the second set of questions, we need to turn to those mechanistic models I briefly described earlier. And because this is a newer approach to studying technological change, I'll provide a little bit more detail. We start by developing a cost model, also known as a cost equation. I'm showing the cost equation developed for silicon photovoltaic modules in the upper right-hand side of this slide. And we start by defining cost as a function of several variables. In the case of this solar PV cost equation, we're saying that the cost of the module, where we take the cost, scale it by the power it provides, is a function of variables like the price of silicon, the efficiency of the module, and the size of the manufacturing plant. And the amount of detail that goes into a cost equation reflects the importance of these different characteristics of the technology and data availability. Given one of these cost models, we can then derive cost change equations. They allow you to quantify a given variable's contribution to change in a technology over time. However, we can't follow technologies continuously through time. We need to compare them between discrete time points, and so we have to employ an approximation. But one major advantage of this approach is that it allows us to disentangle and quantify the impacts of multiple simultaneous changes to a technology when those changes occur in a non-additive fashion. So you might have heard people talk about why silicon photovoltaic modules came down so dramatically in cost over time. Some people point to the increase in energy efficiency. Other people say, oh, well, the price of silicon came down and that was a spillover from other industries. Still others point to the size of the larger manufacturing plants. This approach allows you to actually quantify all of those contributions that occurred simultaneously. This approach also lowers the chance of double counting because you start with a discrete cost model, and it can be used retrospectively and prospectively. Today, we're going to use it retrospectively to understand what led to the improvement we've observed. But because we need to develop a cost model, we all need to have a sense of what goes into a lithium-ion battery. So I'm just going to briefly review it to make sure we're all on the same page. On the right-hand side of this slide, I'm showing a simplified diagram of a lithium-ion battery. On the left, we have a cathode. The classic example is lithium cobalt oxide, but over time, researchers have found ways to replace the cobalt with different mixtures of nickel, manganese, and cobalt. We can also use lithium iron phosphate. On the right-hand side of the diagram, we have the anode. In lithium-ion batteries, this is typically graphite, and this is sheets of carbon. And when you charge your battery, the lithium ions migrate from the cathode to the anode and sit between these sheets of carbon. But of course, the lithium ions don't migrate in a vacuum. They need some help moving back and forth. That help comes in the form of the electrolyte, which is typically a lithium salt like lithium hexafluorophosphate, dissolved in a mixture of organic carbonates. We also have current collectors to help the electrons move back and forth, and they are typically aluminum and copper foil. And then we need to keep the cathode and anode separate with, well, a separator, which is typically made out of polyethylene or polypropylene, sometimes with a coating on top. So given all of this information, as well as more details as to what goes into these components and how the batteries are manufactured, we can set up our cost model for lithium-ion batteries, which I'm showing here. We have different sections for the different components of the battery, and the variables in our cost model reflect the underlying chemistry and engineering, from the specific capacities of the materials to the thickness of the separator. And we also pull out some variables that apply to all of the subcomponents. And this model can be applied to any type of lithium-ion cell. However, in our work, we want to limit our comparison to control for a few factors. Recall how cells diversified over time. We want to control for changes that might have been implemented to make cells better for new, different applications. So we're going to focus only on energy-dense cells, those which aim to provide as much energy as possible in a given volume. And we will control for this volume by comparing cells of only the same size and shape, 18650 size cylindrical cells. Given these controls, we can then examine changes in these variables. We call changes in the variables the low-level mechanisms of cost change. And these are the mechanisms through which the cost of lithium-ion batteries came down in time. However, this is just an equation on a slide. To make this come alive, we need data, a lot of data. So we undertook an immense data collection effort. We collected data from academic articles, corporate reports, legal filings, industry studies, and specification sheets. Our data set includes over 1,000 records, 15,000 qualitative and quantitative data points from about 280 references. On the right here, I've plotted the data we collected for just one of the 41 variables, the price of the metal oxide material in the cathode. And you might note I've highlighted 2 time periods in this plot of price data. These are the periods between which we're going to compare cost change. We're going to compare a representative battery cell from the 1990s to a representative cell from the early 2010s. Within each period, we develop a representative value for each variable, which I plotted here as horizontal lines. We also estimate the data uncertainty for each variable, plotted as the dashed lines above and below the representative values. Given these data and similar data for the other 40 variables, we can quantify the contributions of the low-level mechanisms of cost change. I've aggregated some of those contributions and plotted the results here. We find that the largest contribution to cost change between the late 1990s and early 2010s was the increase in cell charge density, which contributed 38% of the cost reduction observed. The next largest contribution came from the decrease in the price of the cathode material, which contributed 18%. The third largest contribution came from the increase in plant size and the decrease in plant size associated costs, which contributed 14%. We also see significant contributions from a variety of different components, including the prices of the anode, the electrolyte, and the separator. And we see a contribution from increased charge capacity utilization. But when I teach, I try to remind students that if they see discrete bars like this, they should wonder what the uncertainties on the values are. We also wanted to know, and so we looked at the uncertainty estimates for each variable and performed a data-informed sensitivity analysis. The extremes of our uncertainty are plotted here as whiskers. We find that some of our results are really robust to the underlying data uncertainty, like the increase in cell charge density is always the largest contributor. The decrease in cathode material price is nearly always the second largest contributor, but more uncertainty surrounds the impact of the costs that depend on plant size. And these estimates of low-level mechanisms can help those who are conducting research into improving lithium-ion and other electrochemical battery technologies. They suggest which technology characteristics we should focus on. However, not everyone involved in improving these technologies is going to walk into a lab tomorrow and say, I have a great idea for increasing the specific capacity of the cathode material. Some people are going to have different decisions to make, for example, on the designs of policies and the direction of investments. And this research can also inform their efforts. These policy and investment decisions are often associated with high-level mechanisms of cost change, like research and development, learning by doing, and economies of scale. And we can also use our cost and cost change equations to quantify the contributions of these high-level mechanisms to cost reduction. We return to the cost equation and assign each variable to the high-level mechanism that very likely influence a low-level mechanism. And then we can sum the contributions influenced by each high-level mechanism. We've also included a other category because not everything can be assigned perfectly. So we go through and make our assignments and sum the contributions, and the results of that analysis are presented here. We find that between the late 1990s and early 2010s, public and private research and development was the primary contributor to cost reduction. Economies of scale were significant but secondary, contributing about 30%, while public and private research and development contributed 54%. Learning by doing, meanwhile, contributed little. And we wanted to know how robust our assignments were or how robust our conclusions were to the different plausible assignments. So we looked at extreme options, and we find that our ranking is pretty robust. Research and development comes out ahead, and economies of scale is almost always secondary. And we can take this a step further. We can try to ask what fields of research and development contributed. And when we do, we find that advances in chemistry and material science compose the vast majority of the R&D contribution. I should note I'm using chemistry and material science to summarize a broad scope of research, including chemistry, chemical engineering, material synthesis, processing, and characterization. And when we look into these changes and their contributions, we find that multiple cell components and their prices played significant roles. And this partly reflects the fact that cell components could be improved separately and combined in many ways. One lab could be improving a cathode material, another lab could be improving an anode material, and they could still be combined to give a lithium-ion cell without having to reinvent what a lithium-ion cell looks like every single time. So now we want to think about the future. And based on our results, how can we enable further improvement for energy storage technologies? So we can think through our conclusions and the implications of those conclusions. So one conclusion is that we might achieve faster cost declines for stationary applications. And this comes from the fact that when we looked at the learning rates and the other improvement rates, we found that they increased substantially when we included this expanded definition of service that included energy density. And energy density is expected to be less relevant for stationary applications. So some of the efforts that went into improving energy density might be refocused on reducing cost. One implication of this conclusion is that interpretations that are based on measures of past performance might benefit from considering non-cost characteristics. Another conclusion was that increases in charge density contributed substantially to cost decline. So an implication of this is that new battery chemistries should not focus solely on input prices. If someone came to me tomorrow with a great idea to reduce the cost of sodium-ion batteries and said that they could cut the cathode material cost in half, but that charge density improvements were unlikely, and they asked me, would this be okay for stationary applications? I would say, it might be, but would there be a way to also increase charge density? Because that did substantially contribute to the cost reduction we observed for lithium-ion batteries. Another conclusion from our work is that public and private research and development can dominate cost reduction, even after the commercialization of a technology, while economies of scale remain secondary. This reflects the fact that lithium-ion batteries were commercially introduced in 1991. And our study examined a 2-decade period that started years after this introduction. And during this period, R&D was the primary contributor to cost decline. It's important to note that market expansion is itself very important, and it leads to private research and development. But that this private research and development, along with public R&D, was a larger contributor than economies of scale. And so one implication of this conclusion is that we should maintain funding for research and development even after the commercial introduction of a technology. Finally, another conclusion is that access to a diverse chemical space might have enabled batteries to improve rapidly. For example, the fact that researchers found ways to replace the cobalt in lithium cobalt oxide with a variety of combinations of nickel, manganese, and cobalt. And when they did, they didn't need to reinvent the design, the manufacturing, and the operation of these batteries. One can think of these cathode materials as drop-in components. Access to this diversity might have enabled the rapid cost decline we observed. One implication of this is that investments should encourage the exploration of diverse chemistries and materials that can be combined in a modular design. By modular, I mean a technology that allows for components to be improved without needing to be reinvented every time they are. And another implication is that exploring this diversity of chemical options might help reduce the chance of suboptimal lock-in, that we might lock ourselves into lithium-ion technologies while other technologies might be better in the long run for economic, social, or environmental reasons. If we explore diverse options, we reduce the chance of this happening. These are a few of the key takeaways that we hope will inform efforts to accelerate the improvement of energy storage technologies, and I'm happy to answer any questions you might have.
Great, thank you so much, Michael. That was really comprehensive analysis of how lithium-ion batteries have developed over the years. Okay, so we'll do a few questions and answers. I see, Drew, you have a question. Do you want to go right ahead?
Thank you, Mika, for that fantastic overview. I wonder, how do you separate learning by doing from the economy of scale? What's the definition of learning by doing?
That is a great question. So one thing we have the advantage of is we can start with our cost equation, right? And we can assign different variables. But to do this, we need to have very, essentially, very good definitions. And by good, I just mean we apply it consistently. We have to apply a definition of learning by doing that we make very clear in our research. Learning by doing, in this case, we're describing as improvements that occur upon routine kind of manufacturing at the commercial scale. So if you're doing research and development in the lab, that's not learning by doing, according to our definition. If you're doing pilot scale production, you know, a research and development kind of, but at the pilot scale, that's still considered research and development. So our definition of learning by doing is really incremental improvements that are at the commercial scale, which you find in, for example, the yields, right? Increasing the material yield of a material through the process is an example of something that we assign to learning by doing. Meanwhile, economies of scale come from the larger size of the manufacturing plant, which we can separate with our cost equation.
Thank you.
Right, so I had a detailed question on you mentioned the public and private R&D making a big difference here in terms of cost reductions. Are you able to differentiate at all between public versus private R&D?
In the case of lithium-ion batteries, we found this very challenging to do. It's been done, it's been estimated for other technologies, but so much of research and development for lithium-ion batteries has been done in private industry and also in public-private partnerships. It's hard for us to know without more concrete information as to how much funding went into the public and private research and development separately. It's hard for us to disentangle those two influences. With better data and more information, this approach could allow us to do that. We just didn't have essentially the insight into what was going on in private research and development laboratories, and in order to do that.
This makes sense.